Good morning. In this video, we are going to derive the voltage gain of a common source amplifier. Here you can see this circuit has a voltage divider biasing. Already we have completed how to calculate the DC operating point for a common source amplifier using voltage divider biasing. In the circuit, we will derive the small signal voltage gain from a small signal model. First, we have to draw the small signal equivalent of the circuit. So, we know that, so this is gate, drain, and source. This is gate, drain, and source. So, first I will draw the small signal equivalent. Small signal equivalent model. So, the gate and the source is between the gate and the source, that's open circuit. The voltage between can be represented as VGS. Between the drain and the source, there is a current source with GM VGS. There is also R0. If R0 is infinity, we can remove R0. So this is gate, drain, and source. Now we can see here the source. The source is connected to ground. You can see here, this is a source point that is connected to ground. So this source point. So whatever we have drawn till now is for the small signal equivalent of this transistor between the gate, drain, and the source. Now we are going to add the remaining. We have to add the biasing components. So the source is connected to ground. So here the source is connected to ground. And then if you can see the drain, the RD is connected to the one, this part of RD is connected to, one end of RD is connected to drain, other end is connected to the supply VDD. While drawing the small signal equivalent, all the DC voltage source, you have to nullify it. So this VDD is to ground. So from the drain point, there is a RD. The other end of RD is connected to ground. So this is V0. So the drain part is over, source part is over, the remaining is the gate part. So whatever connected, now we are going to just draw whatever connected to the gate. This is the gate. So from the gate, we can see there are two resistors, R1 and R2. This R1 is connected to ground and this R2 is also connected to ground. So from the gate, there are two resistors, R1 connected to ground, R2 is also connected to ground. So which means R1 and R2 are parallel. This is R1 parallel R2 and that is connected to ground. And after that there is a capacitance CC1, coupling capacitance. In drawing the small signal model, we have to short circuit the capacitance. So CC1 is short circuited. After that, a resistance RSI, and this voltage is the small signal input voltage. This is the AC input voltage. So this is the small signal model for this common source amplifier. Now we will derive the voltage gain for the circuit. We can see here what is voltage gain is V0 by Vi, the ratio of output voltage divided by input voltage. So what is this V0? V0 is the voltage across this resistance, parallel combination of R0 and RD. You can see R0 and RD are in parallel. So V0 equal to some current multiplied by the parallel combination of R0 parallel RD. So what is the current flowing through this R naught parallel RD? That is the same as whatever the current flows here, the same current which has to be same as GMVGS. So what is I is equal to GMVGS. Here we have a minus sign. Why there is a minus? Because this is a positive terminal and this is the negative. This is grounded, right? So this is positive and this is negative. So the current direction is from this negative to positive. So there is V naught is minus multiplied by R naught parallel RD. So minus this I is GMVGS R naught parallel RD. So this is V naught. On the other end, what is this Vi? So here is the input voltage Vi. Now, what is VGS? This is VGS. So VGS is certainly the voltage across this resistance R1 parallel R2. Now applying a voltage division rule, what is VGS is? We can refer to voltage division rule. So VGS is total voltage, which is VI multiplied by R1 parallel R2 divided by RSI plus R1 parallel R2. This is VGS. So from this we can derive what is VI. VI is VGS multiplied by this component divided by R1 parallel R2. So what is AV equal to V naught by Vi. So V naught is minus GM VGS R naught parallel RD divided by what is Vi. So Vi is VGS multiplied by RSI plus R1 parallel R2 multiplied by R1 parallel R2 here. Now this VGS will get cancelled. So what is voltage gain is minus GM R0 parallel RD R1 parallel R2 divided by RSI plus R1 parallel R2. So this is the voltage gain of a common source amplifier. Here in the circuit there is no source resistance. So now we will derive the voltage gain of a circuit including the source resistance. So now we will start to derive the voltage gain of a common source amplifier with the source resistance Rs. You can see there is Rs and here there is positive and negative supply voltages. For the same circuit already we have derived, we have posted a video how to derive the DC operating point. Now we will do the small signal analysis. So we are going to draw the small signal equivalent circuit. So this is gate, drain, and this point is source. So gate, drain, and source. We know that between the gate and the source we are having an open circuit. The voltage across this is VGS. Between the drain and the source is a current source, dependent current source of value GM VGS. Now we will assume R naught as infinite. R naught is infinite, so we will remove R naught here. In the previous case, the source is directly connected to ground, so we have connected the source to ground. Now in this case, the source is not connected to ground. There is a resistance Rs. This is connected to minus 5 volt. While drawing the small signal model, this DC source has to be nullified. So that has to be connected to ground. So from the source, we are having a Rs. The other end of Rs is connected to ground. Now if you see the drain part, so from the drain part there is a coupling capacitance that is short circuited, that has to be short circuited in small signal model. From the drain there is a RL, the RL is connected to ground. The same thing I am going to draw here. From the drain there is a RL, the other end of RL is connected to ground. So you should not connect the other end of RL to source here. It has to be noted the other end of RL must be connected to ground. So other end of RL is connected to ground and this is connected. This is B0. So now seeing here there is another resistance RD. The other end of RD is connected to here. In the DC model it is plus 5 volt. While drawing the small signal model it has to connect it to ground. So there is other RD from this drain to ground which will come in parallel with this RL. So together I can write this is RL parallel with RD. And to the gate side, to the gate there is a RG, gate resist RG connected to ground. After that the input, small signal input voltage Vi. So this is a small signal equivalent model. So the whatever I have drawn in blue color, this VGS and GM-VGS is common for all the MOSFET. This is a small signal model of the MOSFET. To that, whatever I have drawn in green color is for the biasing circuit. Now we will derive the small signal model. We know that voltage gain AV is the ratio of output voltage divided by input voltage. So what is V0? So V0 is the voltage across this resistance RL parallel RD. So some current multiplied by this resistance RD parallel RL. We can see that the direction of the current, this is plus and this is minus. Okay. So the current, whatever the current flows through this resistance, the same amount of current, which is GM-VGS. So the current is minus GM-VGS RD parallel RL. Now to the input side, we have to calculate what is Vi. So Vi is the input voltage. This is RG, the gate resistance. Oh, okay. Now this is plus, this is minus. Now I'm going to write a KVL loop here. So this is source resistance. I will write a KVL loop for this minus Vi. So starting from here, minus Vi plus VGS plus this Vs. What is Vs? Is the voltage across this resistor. Let me name it as Vs. Plus Vs equal to 0. So I have written a KVL loop. This forms a closed loop. Okay. Minus Vi, VGS. So this is a loop. Minus Vi and then a VGS and plus Vs equal to 0. So we know that minus Vi plus VGS. So what is Vs? Vs is the voltage across this resistance Rs. So current multiplied by resistance. What is the current through Vs? The current through this resistance Rs is the GM-VGS. So this current, the same amount of current will flow here because this side it's an open circuit. Here the current is 0 because it's an open circuit. So whatever the current comes here, the GM-VGS, the entire current will flow through the resistance Rs. So Vs is GM-VGS multiplied by the resistance Rs equal to 0. So from this we can write what is Vi. Vi equal to VGS multiplied by 1 plus GM-Rs. So we have derived what is V0 and what is Vi. Now the voltage gain AV is minus GM RD parallel RL divided by 1 plus GMRS. So this is the voltage gain for this circuit. So as a continuation, now we are going to derive the voltage gain for this circuit, which has a current source and also a bypass capacitance. We'll start with this is the gate, drain and source. So gate, drain and source. So between the gate and the source there is open circuit. The voltage across the open circuit is VGS. Between the drain and the source, GM-VGS. Assume R naught as infinite. So this is the small signal model, small signal equivalent for this transistor. Now to the drain side there is a resistance RD. The other end of RD here in DC model 5 volts. So in small signal model that has to be connected to nullify, so connected to ground. From the drain there is a resistance RD. The other end of RD is connected to ground. So this drain, here is the output voltage V0. Here is the output voltage V0. Now to the source side, you can see there is a current source, a DC current source, and there is a minus 5 volt connected here, and here is a capacitance. So in the small signal model, the capacitance has to be short circuited. So if you short circuit this capacitance, it means the source is directly connected to ground. So I can connect the source to ground. To the gate side, there is a gate resistance RG. RG is connected to ground, and there is a small signal input voltage Vi. So now this is the small signal equivalent model. For this, derive the voltage gain. What is AV is ratio of output voltage divided by input voltage. In the circuit, what is V0? V0 is the voltage across this resistor RD. You know that. This is the direction of the current. So the whatever the current flow through RD, this is equal to GM-VGS. So V0 is minus GM-VGS RD. Minus GM-VGS RD. Now what is Vi? You can see Vi is equal to VGS because they are connected to the same nodes. The source is grounded and this is the same node. So Vi is equal to VGS. Vi equal to VGS. Voltage gain is minus GM-VGS. VGS will cancel, so I can write voltage gain is minus GM-RD. Thank you. In the next video, we will discuss the short circuit current gain and Miller capacitance.